Good morning, good afternoon, good evening. Today I'll be showing you how to make this tile roll text effect. Texted tile will bounce, spin, and roll around to form a readable text at the end. It's one of those animations that's a hell to recreate manually, so as always, we'll automate it with geometry nodes. I'll be spending the vast majority of this video going over how to create this rolling physics with simulation zone. It's a long episode and I'll be skipping over some details, so let me know in the comments if you have questions. Alright, let's get started. Before we hop into the node tree, let me start with some explanation. We'll be making tiles bounce and roll, but it's not going to be using proper rigid body physics. If we want to emulate proper physics, we'll have to account for multiple states and attributes like inertia, solve EOM full of differential equations, and simultaneously output multiple variables. Unfortunately, my less than 8-bit brain processor lacks power for such task. So, what I'll be showing you today will be makeshift physics at best. We'll consider 3 different behaviors for this tile rolling physics. First, free-falling behavior without ground contact. Second is bouncing back and spinning behavior upon ground collision. Lastly, rolling or falling over behavior at low velocity. We'll calculate these physical behaviors separately to emulate rigid body physics. Though it is makeshift physics, I think they look decent both in 2D and 3D objects, but you can be the judge of that. Now, I won't be covering object-to-object collision because that is too much work in itself. Okay, let's get started. As soon as we enter Blender, we'll hop right into Geometry Nodes layout. A to select all, X to delete. Shift A, add mesh plane. Click on New for map, then delete group input. We'll add a grid instead. This will be our starting point. I want this facing front with z-axis down, so add a transform geometry. And enter 90 in X to make it stand up. Go to front orthographic view using numpad 1 and 5. Then convert the grid with geometry to instance. We won't be using point physics since we need the actual mesh to detect collisions, but we want to keep the motion calculation simple by using instances. Next, we'll prepare some attributes we need for our physics. Add a store named attribute and change dropdown to vector and instance. Name it vel for velocity. Duplicate the store named attribute and name it omega for angular velocity. Next, add a translate instance to control position. Disable local space for global positioning. Lastly, add a rotate instance to control its angle. We want to update these each frame, so add a simulation zone, then reconnect. Select these 4 nodes to duplicate into the simulation zone and reconnect. These ones on the left are for initialization, ones in simulation are for update. Let's start by creating a freefall behavior. We actually don't want to update omega during freefall, so Alt-X to delete. We'll first start with the velocity. Add a named attribute vel. Connect to vector mass add. Then connect the vector mass scale to bottom socket. Enter the gravitational acceleration of negative 9.81 to z. Then connect delta time to scale. Use the add result as vel for current frame. Select these 3 nodes and Ctrl G to group. Tab out and rename to calc vel ff. ff for freefall. Next, position. Add a named attribute vel. Connect to vector mass scale. Scale it by delta time and connect to translation. Lastly, angle. Add a named attribute omega. Pass it through vector mass scale. Scale with delta time and use as rotation. We're done with the free-falling portion. Let's test it out by entering 2 meters in initial z translation. We can also add some y omega as well. Running the animation will result in this grid falling as it spins. Okay, let's reset the omega back to 0, but keep the translation as 2 meters. I'll also add 30 degrees in Y rotation for ease of future explanation. Now, before we start thinking of collision, let's pretend that we have a ground plane at Y equals 0. So the red X line is our ground plane. I don't want the grid, or I'll just call it a tile, falling below this red line. So let's add a positional adjustment right here. To do so, we want to find the lowest point, the point of contact of this tile. So branch out a realize instance after rotate. Then attribute statistic after realize. Add a position node and separate its XYZ. Connect Z to attribute. Using a compare equals, compare min and Z from separate XYZ to find all points with lowest Z value. Branch out another attribute statistic from realize and change type to vector. Connect the compare result to selection. Then position to attribute. Now we should be able to find the mean position of points with lowest Z. In this case, since only one point fits the description, this point position is outputted. Now disconnect only the geometry connection. Then select these nodes to group them. Reorganize a little. Then tab out and call it Get Contact Point. We'll be reusing this node group a lot, so make sure to create it. Now that we know the lowest position, we can adjust mesh position to stay above ground. Connect a separate XYZ. Then Z to math subtract. Alt S to switch the top and bottom socket, and enter 0 for the top value. Connect the mass maximum to max with 0. Use it as a Z value for combine XYZ. Insert a translate instance before simulation output. Disable local and connect combine result to translation. We can confirm that the tile won't drop below the red line by running the animation. Let's now select these nodes and group them. Reorganize a little. Tab out and call it Adjust Pause. Now that tile is guaranteed to stay above ground, let's start working on ground collision. We first want to judge if the tile is hitting the ground at the current frame. I'll start making it in the space above. Add the Get Contact Point group we made earlier. Then connect to rotate. Separate XYZ the result. Connect Z to less than or equal and compare to 0. Then pull out a switch and reconnect like so. False means it's above the ground, so tile is in freefall. True is colliding state, but we'll use a rotate result as a starting point. Insert a reroute and Ctrl G to group by itself. We'll just delete the reroute once a node group is made. Exit out with tab and rename it to ground collision. And reorganize a bit. Let's go back into node group to make the collision portion. First, we'll consider the linear movement upon colliding. When the center of mass is offsetted from the point of collision, there is a reactive force applied towards the center from ground. In the case of this illustration, the tile will bounce off to the left due to the reactive force. We'll need two vectors to calculate this: velocity and directional vector from contact to center. We should end up with the resulting vector going towards top left. Start with a store named attribute and set it to vector instance to update vel. Next, add a named attribute vel for current velocity. You'll need to manually set the dropdown to vector if it does not appear automatically. Connect to vector mass reflect to reflect it off a plane. The bottom value should be the plane normal to be reflected off of. And that can be calculated by subtracting contact point from the position. Let's plug this into store named attribute. We can see that the tile bounces towards left, and further increases its leftward motion as it bounces with updated velocity. Let's dampen the effect as it bounces by adding a vector mass scale. Enter 0.8 to reduce its effect each time it bounces. It should slow down but still move indefinitely. This will be corrected later, so we'll roll with this for now. Now, select these nodes and group them. Connect the group input to the scale to control it externally. Call it damp factor. Tab out and name this calc vel C, C for collision. Next, let's consider the effect it has on rotation. Upon colliding, torque acting on center will be generated perpendicular to the point of contact. In this case, there will be a counterclockwise rotation due to the contact point being on the right of the center. To calculate this rotation, we'll need velocity and this vector just as before. Let's emulate the rotation generated by this torque now. Duplicate the store named attribute and move it to the left. Change the name to omega. First, get the vector connecting center and contact by subtracting get contact point from position. Use a vector mass cross product with named attribute vel to get the axes of rotation. If we plug this into omega, we can verify that the tile rotates as it bounces. However, this rotation should depend on the colliding velocity. So let's add a normalize after cross product to get its unit vector. Then, insert a vector mass scale. We'll grab the magnitude of velocity by taking the lengths and use it for a scale value. Now the resulting rotation after collision will depend on the collision velocity. Let's add another vector mass scale to emulate different rotational inertia. High value results in fast rotation of a light object. And you can set it to low value if you want an object to appear heavy with high rotational inertia. I'll set this to 1 for this video, but you can choose any value you like. We'll select these nodes and group them. We'll also turn the scale value into argument. Call it omega gain. Tab out and rename it calc omega C. We made the bouncing and spinning motion, but this last part feels kinda weird. It's falling to the ground slowly and awkwardly. Well, this falling behavior follows a different physical property than that of bouncing. When an object lacks velocity to move its mass, it should instead follow a rolling behavior, with gravity pulling down on its center of mass. Resulting rotation should center around ground contact, causing object to fall to the ground. To replicate that, we'll start off by making a low speed decision. Add a named attribute vel and connect to vector mass lengths. We'll use a less than to compare with constant, which I'll just use 1. We want to use this compare, but geometry switch only accepts single value, whereas this result is a field. So let's first pass it through a sample index. Connect dropdown to boolean and instance, and connect less than result to value. Reconnect to switch to avoid error. We'll reconnect to the geometry socket like so. As a matter of fact, let's also connect true as well. Add a reroute and turn it into node group as before. Then delete the reroute and tab to exit. We'll just call this rolling. Let's hop back in it to work on the following algorithm. I want to start off by stopping calculation based on center of mass. So add a store named attribute vel and omega to reset their values. This should stop the tile from bouncing or spinning. Next, to realize rotation based on ground contact, add a rotate instance and turn off local space. We'll use a ground contact as pivot point. Add a group input and connect a get contact point. Plug it into pivot. We'll get the rotational axes next. The two vectors we need for this are the vector from contact to center and the ground normal. Subtract ground contact from position to get the first vector. Connect to cross product, Alt S to flip its inputs, and enter 1 into Z for the ground normal. We'll pass it through vector mass scale and use it for rotation. We want to emulate falling behavior by changing the scale value based on how far it has fallen over. But how can we define if the tile has fallen flat on its side using what we have? Well, we know the side of this tile is 1 meter in length. So if the z height of this vector is at 0.5, we can consider it grounded. As converse, the highest z value will be square root of 2 over 2. That is when the tile is standing upright on one corner. So, we'll just use these as indicator of falling state. Connect a map range from scale. Then pull out a separate XYZ from subtract. And use Z to drive the map range. Set 0.5 for from min and square root of 2 over 2 for from max. .5 for 2 max should be good for falling over result. When we run the animation, we can see that the tile falls to the ground after several bounces. I think it looks decent. Right, the physics part is pretty much done. I'll just reorganize a bit. Go back to the top layer and we'll try it out with different parameter. Increase the initial Z position and also add a bit more rotation. Animation looks decent. I think I'll give it a passing grade. Let's now try this with multiple tiles. To do that, let's add a duplicate element after geometry to instance and increase its instance amounts. They are currently overlapping, so let's add a random initial angle per instance. From rotate instance, connect the combine XYZ. Connect the random value from a Y rotation, then enter tile for max and use index for ID. Now that initial angles are all different, let's run the animation. They seem to be all stuck together. We need to update the simulation per instance if we want them to have individual physics. So create some space after simulation input and add it for each element node. Change the main to instance and reconnect. Output should be placed right before simulation output. Alright, all the tiles will now move separately. Now that the physics part is complete, let's make some texted tiles. But before we do that, let's select these nodes from store named attribute to simulation output and group them. We'll free up some real estate this way. Call this node group tile roll. Though we can probably use textures to make texted tiles, I'll just create them with geometry nodes. So let's delete these nodes on the left and leave only the tile roll and group output. Add a string input. Enter T and pass it through strings to curve, then output. Currently we are in the front view, so we have to rotate the viewport to display it. Go to top orthographic view with numpad 7. First, we want this left shifted to the center. To do that, add a set position. Change the pivot point on strings to curve to midpoint, and from pivot point socket, connect the vector mass scale. Scale it by -1, then to set position, position. This should center the letter. Next, realize a curve and fill curve to convert to mesh. Either type will work. Let's extrude the letter a bit so it's not entirely covered by the tile. 0.01 should give enough offset. Add a grid and join these two together. The letter has blended into the tile, so let's quickly set a material so we can view it. Choose a default material and open up a shader editor. Select the default material. I'll just set it to black RGB. Set the 3D viewport to material preview to display the text. Let's now switch back to geometry node editor and continue. Insert a transform geometry after join and rotate by 90 degrees on X. Make it face front with Z down. Then use geometry to instance to convert to instance. We'll repeat this tile formation per letter instance. So add a for each element node and change the main to instance. Then connect them up like so. Now we can enter multiple letters, so enter test. They're all overlapping, but we can confirm there are 4 instances in the spreadsheet. Let's select everything in the for each element and group them. This input order seems to be switched, so I'll just fix that. Tab out and name it Make Text Tiles. Place tile roll back in and reorganize. All the tiles should be hovering above at initial position on frame 1. Run the animation and we now see the textiles bouncing around as before. Since this is a text animation, We want to make sure that text tiles are readable at the end. So I'm going to use a technique I call bake and offset. We'll bake the end location and offset them from the start. To do so, we want to specify where the tiles should end up before simulation. I'll remove the tile roll group for now. Let's arrange the tiles so the text is readable. Insert a translate instance and disable local. Connect the combine XYZ to translation. Then connect index to X to shift letters to the right. Let's also add some gaps by inserting a multiply with 1.1 as value. I don't want the tiles in the same Y location, so let's also plug the multiply result into Y. This way, tiles and letters won't overlap during animation. This depth should not be an issue if we render out with orthographic camera. We'll store this final position as an attribute. So add a store named attribute and change the vector instance with name pos f. Store the current position. Then reinsert the tile roll group and run the animation from frame 1. It's kinda long, so let me just set the end frame to 200. After we complete the animation run through, go to the final frame. Then branch out a bake node from tile roll and bake the 200th frame. Add the named attribute pos f we just stored, and pull out a sample index of vector and instance from bake. We'll sample position of each instance index. Vector mask subtract the sampled position from pos f. And add translate instance with local off to offset the result. Now all the tiles should end up at the pos f we specified after they bounce around. Let's set their rotation as well. Initial angle is already set at a readable angle, so attribute storing is not necessary. Ctrl-Shift-D to duplicate the sample index with connections. Then, change vector to quaternion. We'll sample instance rotation instead of position. Then, invert it using invert rotation. Plug it into rotate instance rotation. Now all the textiles should end up at a readable state after all the physics converges. We can now enter any text we like. Just make sure to rebake after one run-through of the animation. Alright, this is the end result. Okay, let's review what we made. This is the top layer. Here's make textiles. Tile roll. from the left. CalcVel FF. Get contact point. Ground collision. Calc omega C. CalcVel C. Rolling. Lastly, adjust pause. That's it for this one. You can play around with initial position, velocity, and rotation, as well as damp factor and omega gain for different looks. Though this is a makeshift physics with a lot of flaws, we can use pretty much the same logic to roll around a cube as well. I might have a chance to show it to you in later videos. Alright, thank you for watching, and see you in the next one.